Question of what black holes are and what they do begins with the life cycle of a star. Black holes don't come out of nowhere. To understand what they are, we need to get a sense of where they came from. The life cycle of a star starts with a nebula, which is Latin for a formless blob of space dust, gas, schmutz, ice crystals, neural hydrogen, etc., spinning gently in the vastness of space. In the unit on rotation we just finished, we talked about conservation of angular momentum, the fact that anything that starts spinning will keep spinning in the same direction and the same orientation until an outside torque interferes. We also talked about center of mass and the idea that if a force goes through the center of mass, it will not provide a torque, and if a force doesn't go through the center of mass, it will provide a torque and the object will start to spin. We talked about the probability that every single force since the dawn of time has gone right through the center of mass of this cloud and decided that we're all but certain it will be spinning. And it will stay spinning in the same direction until an outside force causes it to clump up. Gravity is probably our number one culprit, a passing gravitational disturbance, some nearby mass passing by, or a shock wave from a supernova hundreds of light years away. Some force field causes some of the matter in the cloud to clump together. Bigger clumps have more mass. More mass means more gravitational force, means a stronger pull to the other clumps of mass. The clumps of mass will move toward each other, and the cloud will contract. As the mass contracts, conservation of angular momentum causes it to spin faster and faster, like an ice skater pulling her arms in, causing her rate of rotation to dramatically increase. Now, picture a blob of clay in your hand. If you spin it faster and faster and faster in your hand, sure enough, you're going to smush it more and more and more together. The cloud will contract further, then it will spin faster. The cloud will spin faster, therefore it will contract further. As the effect spins out of control, it is completely run away, and chemistry reminds us from our basic gas laws that as the volume is condensed and the pressure is increased, the temperature goes way, way, way up. There are two shapes that you can make if you're spinning a formless blob of clay in your hands very fast. If the pressure is even on all sides, you'll spin it into a ball, aka a sphere. If the pressure is mainly top and bottom and everything else evens out, you'll spin it into a pancake or a disc. In space, there's no reason to favor one setup over the other. We'll get both. The clump flattens out into a disk with a big, hot, dense core in the center. We'll call this core a protostar. Again, it spins faster and contracts and spins faster as the temperature soars until we hit the magic number. And the magic number is 7 million Kelvin. At that number of degrees, the star has enough energy to begin the fusion of hydrogen. Hydrogen plus hydrogen equals helium in a huge nuclear reaction. The binding energy that keeps hydrogen and keeps individual nuclei separate is released in a huge surge of power. The reaction is absolutely explosive. It is the kind of nuclear reaction that leaves human nukes, that is nuclear fission, the decay of things like uranium and plutonium, in the dust. If we could run nuclear fusion on this planet, it would be exactly as Doc Ock in Spider-Man says, the power of the sun in the palm of your hand. The isotope of hydrogen in 1 cubic centimeter of seawater could provide enough power just from that seawater to fulfill the electrical needs of a large metro area for a year. That's how much energy we're talking about is released here. The explosion is literally out of this world. As the reaction begins and the star ignites, 2 massive jets of gas are released. Now, why 2? Let's say there's only 1. What's the initial momentum of the protostar? Got it? Okay. Well, send 1 jet this way. What would happen to the star? We can't violate conservation of momentum. What's more, trying to balance this momentum with that, well, literally, it's not going to happen. Bipolar jets, conservation of momentum. 1 jet of gas goes this way, 1 jet of gas goes that way. Total momentum 0. This is how we can see a star igniting in space. If we look through our radio telescopes and we see a star or a galaxy, with these two jets in opposite directions of equal amounts of matter streaming out, we know a tremendous explosion is taking place and a star is being born. Interesting point, anything that's heavy enough to have any inertia at all is going to be blown outward in the force of this explosion, and that's disproportionately going to be all the heavier elements that are knocking around already. Those mass chunks, those bits of gas and dust and ice and schmutz blown outward are going to stay in the neighborhood of the star. If they get close enough to other mass, they'll feel a gravitational attraction. Gravity will clump them together bit by bit, and those clumps over time may yet have the gravitational pull to form themselves into planets. Closer to the star, you'll have more gravitational pull. The mass will be pulled closer together and form solid and liquid planets like Mercury, Venus, Earth, and Mars. Further out, there isn't as much gravitational pull, and you will get the gas giants. The star, meanwhile, has continued burning merrily as a giant nuclear fusion power plant. Hydrogen fuses into helium, releasing thermal energy, electromagnetic energy, and nuclear energy of every kind. The star continues to burn under its own convection. Its own gravitational pull ensures that more matter gets pulled into the core, where the strongest gravitational force is coming from, providing new opportunities for fusion and raising the internal temperature even further. This goes on for billions and billions and billions of years until the star runs out of fuel. Hydrogen is finite. Sooner or later, after millions of millennia, that star is going to burn through all the hydrogen that was present in the original nebula. As the reaction dies down, the outer layers begin to expand and heat up now that there's no longer as much of a chemical reaction happening in the core. We'll call this star a red giant. When our sun, in the fullness of time, becomes a red giant, then the sun will be so big that Jupiter will be the closest planet to the sun, and the area previously taken up by Mercury, Venus, Earth, Mars, and part of the asteroid belt will be inside its interior. The asteroid belt, by the way, was supposed to be the fifth planet, but never did get close enough to other mass to have enough gravitational pull to hold it together as a solid planet. It's no great coincidence that Mars is the last of the solid planets with enough gravitational pull to stick it together in the first place, and the next planet out is Jupiter, the gas giant that never had enough gravitational pull to clump the solids in. By the way, in case you're worried about this happening anytime soon, please note that human civilization, the ability to make moral choices and to use any tool complicated enough that it couldn't have been invented by an anteater, who are very clever critters with tools, at least as far as the ants go, is 6,000 years. The Jewish calendar that you see on the top of our e-news is not counting from the Big Bang. It's counting from the first Shabbat, from the invention of humanity. The distinction between animals, whose goal it is to stay uneaten and to have their offspring be uneaten, and humans that have a spirit from God, whose goal it is not to raise uneaten children, but good children. There's a distinction, a moral distinction, and that's what the Jewish calendar is counting from, and I'd say about 6,000 years of human civilization, or 5,700 and what's-this, sounds about right. Now, compare that 6,000 years going from cave people with meat on sticks and early vegetarians with giant carrots returning from the kill to iPads and politicians in Washington. Now, that's 10 to the third. So we could go from cave people to our current politicians. Yeah, I know there's not much of a difference. 1,000,000 times over before we start to worry about these kinds of astronomical effects. Now the star begins burning the heavier elements, and next heavier than hydrogen is helium. Let's see, hydrogen, helium, lithium, beryllium. We are ready to fuse two heliums to make a beryllium. What happens when the star runs out of helium? Well, what happens next depends on the size of the star. To answer the question, does it have enough energy to burn heavier elements than helium? Our sun is a very small star. I'm sorry, in the grand scheme of galactic politics, we are nothing. We are podunk in the western spiral arm of the galaxy. Yeah, I know we think our sun is big and bright, but on a galactic scheme, it doesn't amount to anything. When a small star runs out of helium, game's over, insert quarters. It ejects more gas and dust as the reaction dies down, and it expands, and more volume means less temperature, thank you chemistry gas laws, and cools. And because it cools, again it expands and expands and cools into a planetary nebula. The nebula has a core in the middle that we're going to call a white dwarf, which cools and spins and spins and cools. As it further cools and its energy output reduces, among other things, it'll become harder to see, and we'll call it a black dwarf. The core that once used to be a star and is now surrounded by a thick cloud of cooling, spinning, ejected gas spins and cools gently in space. Perhaps a gravitational disturbance will set the nebula clumping and contracting and spinning faster again. Sound familiar? That's why we call it a life cycle. Now, what about a larger star? A larger star is defined as a star that has energy to burn through all of its helium and then burn the heavier elements. It can burn carbon, oxygen, neon, magnesium, everything up to iron. Iron is the end of the line. There isn't enough thermal energy in the universe to make two irons fuse into anything heavier. Having burned the whole core into iron, the star can burn nothing else. The reaction ends spectacularly, and the dying star collapses into itself as protons and electrons fuse into neutrons, the heaviest atomic material there is, and then explodes as its temperature soars. Neutrons are not stable. Think chemistry. You want to make something unstable and radioactive? Take it, add a lot of neutrons to make a new isotope. We've converted the whole star through high temperature and pressure into neutrons. It is hot, it is dense, it is unstable, and it is explosive. We'll call that explosion a nova. Once the nova has blown everything in the region to kingdom come, a super dense, supermassive material, denser than any matter that we have ever encountered, why? Because it's mainly neutrons, is all that remains of the star's core, cooling and condensing into space. A particularly enormous star will have a super big explosion, and we'll call this a supernova. This explosion is so catastrophic it will wipe out everything in the region, and what will it leave behind? Think about it. If a regular nova leaves behind a hot, dense, supermassive core of dead star, what would a supernova leave behind? Logic dictates it should be a super hot, supermassive, super dense clump of cooling stellar core, and that's exactly what it is. What was it? Mainly neutrons. All that mass is still there, spinning and cooling in the darkness of space.